Then let me start sharing my screen. You see my slides, right?
Yes, it's fine.
Yes, sir.
Okay, perfect. All right, then, yeah, welcome and good evening to India. Welcome to the fifth lecture on modern synchrotrons and free electron lasers. So we are still stuck with modern synchrotrons, but next week, I assure you, we will get to the free electron lasers as well. And you will see anyway that many components of synchrotrons are just the same or just upgraded versions of the components that are used in synchrotrons. So it definitely makes sense to go through these different devices and through the physics that is the basis of synchrotrons, because is all very similar for free electron lasers. So today's lecture is mainly focused on beamlines and beamline optics. This diagram or this representation we have seen last time already. So this actually nicely summarizes the very most important components that make up a modern synchrotron. And last time we basically followed the path of the electrons, starting from the electron gun, where the electron beam is produced, going through some accelerator stage. This can be just a linear radio frequency accelerator, which we have looked at. It can also be something slightly more involved, like a microtron or racetrack microtron. So these are just like more simple versions of electron accelerators to speed up the electrons and get them closer to the final speed that is needed for storing them in the main storage ring. And yeah, we talked about so that this has to be done in several stages. So there's this pre-acceleration stage like a LINAC, then there is a booster ring. The booster ring is an actual synchrotron. Yeah, remember that the name synchrotron indicates that it is some kind of device where something is synchronized. And a synchrotron is actually a ring accelerator where acceleration and confinement of the electron beam by the magnets is synchronized in such a way that at the same time the energy of the electrons is increased, but the magnetic field strength that confines the electrons on the orbit is also ramped up, such that the electrons are kept on the same stable orbit, which is different compared to the microtrons, for example, that we looked at last time, where by accelerating the electron beam, maybe you remember that the radius of the electron orbit in this constant magnetic field kept growing and growing in the microtron until the electrons actually circled around at such a large radius that they would actually leave the accelerator and then come out as the final beam. But in a synchrotron, acceleration and confinement is synchronized so that the electrons orbit around many times to gain energy before they are then finally injected into the electron storage ring. And that is not actually a synchrotron in the sense that the both energy and magnetic field confinement are actually kept constant. Nevertheless, there is an radio frequency acceleration stage, which is just needed to constantly feed back energy into the electron beam because the electrons also constantly lose energy. Why do they lose energy? Well, because they emit synchrotron radiation. That's the whole point of storing electrons in the storage ring. And they lose energy by emitting synchrotron radiation on every magnetic device. On every bending magnet, they emit radiation, and in particular in these insertion devices, which can be wigglers or undulators, which are these dedicated emitters of synchrotron radiation. Of course, there they lose a lot of energy, and that to compensate for these losses, the beam needs to be constantly re-accelerated. And yeah, so main synchrotron radiation sources are these undulators, but still even just bending magnets, where just the electron beam is bent around the corner, are still used as synchrotron light sources, which have typically very broad spectrum, but a broad spectrum of radiation up to the X-ray range can be very useful for many applications. For example, if you want to just record a absorption spectrum of some sample where you want to then see absorption dips, like lines in a wide range of wavelengths, for example. Yeah, today it's about the beamline. So after so behind the electron beam is kept inside the storage ring, but the photons emitted, they come out and travel into the beamline, and then let's see what different elements the photons meet on their path through the beamline. Just before that, a very brief recap what happens in the undulator, because that is really the heart of every synchrotron and free electron laser. It's the undulator that emits the radiation, and we talked about that already the past 2 sessions. Just as a recap, undulator radiation is quite narrow band. Yeah, it comes in these sharp peaks in the photon energy spectrum. And the peak labeled number 1, that's what we call the fundamental or the first harmonic, which is such a sharp emission peak. Remember, this is all due to constructive and destructive interference of the partial beams emitted in every undulator period. So we get these orders of constructive interference, first order, second order, third order, very similar to interference at a multi-slit arrangement, where you would get interference on as a spatial pattern of bright spots on a screen. Here, interference happens in the longitudinal direction along the electron beam, but still interference happens, which manifests itself in these diffraction or constructive interference orders, first order, second order, and so on. And yeah, the 4th generation synchrotron, that's synchrotrons where the electron beam is very tightly confined by improved design of the storage ring. So stronger magnetic field confinement, better design of the like arrangement of the components to have very stiff confinement of the electron beam, and that leads to higher brilliance, like peak brilliance on the different orders, and also yeah, and so higher peak brilliance and sharper, like spectrally more narrow emission peaks. But we will see that this looks very sharp and narrow, but if we actually zoom into this region, we will see that each order or each harmonic, even the fundamental here, actually still has quite a broad emission spectrum, at least broad compared to typical atomic transitions or ionization edges in atoms and molecules, which can be much sharper than that. So in the end, we will see that we will have to add additional devices that make this light that's emitted even on just one harmonic even more monochromatic for many applications. Then last time we also had a look at one example undulator. This is undulator 32 of Petra 3. That's a very large storage ring at DESY in Hamburg. And we actually using this what is called the undulator equation. We calculated the maximum wavelength, minimum photon energy. This is like angstrom range and kilo electron volt energies. And we also discussed the formula and the way to calculate the emitted power from such a device. And just without, we won't repeat the whole thing, just remember from 1-2 meter long undulator like this, we expect power emitted in the range of several kilowatt. So this is quite intense X-ray radiation. And that has consequences for the subsequent beamline that has to somehow deal with this huge amount of X-ray power. Yeah, so this is a typical sketch of a X-ray beamline. On the very left, top left here, this is the source, the undulator, which emits a divergent beam of undulator radiation. Right, there is an angle dependence. If you remember, there's this theta term. There is a term dependent on the magnetic field, and so in the end, we get this radiation made up of various harmonics, and even each harmonic has some finite spectral width and divergence. So the first element is to somehow shape, like skim out of this quite divergent and very intense beam a central part, which is like less divergent, so we can better transport it through the whole beamline up to the sample. And so we have initially a BPM, that's a beam profile monitor, to get some first idea of what is the profile of the beam, then some beam defining apertures and also filters to very broadly filter the radiation. To, like, for example, if this is supposed to be a hard X-ray beamline, then we want to get rid of any long wavelength radiation, like even visible and soft X-ray light would be disturbing. So we would like first like coarsely shape the beam, both spectrally and spatially, also with some slit arrangement. And then typical synchrotron beamlines have focusing optics. So this arrangement of these plates, you can see, this is a combination of mirrors typically to bend the beam and also to focus the beam. And most beamlines have what is called a monochromator, which is a device that further narrows down the spectrum of the undulator radiation. So it monochromatizes the radiation further. And then there's additional slits to like nicely cut out only the central intense part of the beam to avoid any radiation on the sides that might cause scattered light, that might cause ionization and emission of electrons from the walls of the vacuum chambers and these kind of things. There's additional beam intensity and also beam profile monitors downstream before, in the end, usually we focus the light onto the sample. And then depending on which technique is to be used, we would either detect the light that is scattered or that's transmitted, or we would detect emitted electrons, ions. Yeah, mainly it's that. So it's either we detect the light or we detect the products from the interaction, which is electrons and ions typically, possibly also some chemical products. So if we start from the very beginning, like the BPM, that's a beam profile monitor. These can be very simple devices. In the simplest case, this would be just a thin wire, which can be moved through the beam. So typically this is a tungsten or some refractory material, very thin wire. And the way it works is that when the X-rays hit the wire, they would photoemit electrons, right, by Einstein's famous photoelectric effect. And by emitting photoelectrons out of the surface, basically the wire charges up positively because electrons are negative, they go away. What's left behind is positive charges. So we could then detect a very weak current because electrons would basically flow from the power supply, from the source back into the wire where the electrons are lost by photo emission. So yeah, typically there's plenty of what is called picoampere meters. So devices that can measure very weak currents all around these synchrotron beamlines because yeah, synchrotron radiation tends to emit electrons from all sorts of wires or surfaces, which always gives a nice way to measure the intensity, or in this case, the beam profile when we move this wire across the beam. Of course, this gives only a one-dimensional cut through the beam. There's better ways to get two-dimensional information, also very simple. These would be just metal blades that are moved in vertically or horizontally. And then by cutting into the beam, we would start emitting electrons from the blades, which can be measured as a current, just like in the wire case. And then by measuring differentially the currents going into left and right and up and down blades, this gives us a measure of like the width of and the transverse profile of the beam, and also the position, of course. Or even better, to really get something like a picture, an intensity profile of the beam would be, for example, these two-dimensional diamond, very thin deposited layer on some substrate that, of course, needs very high heat conductivity, because there's a high heat load on these elements at what is called the front end of the synchrotron beamline. So the front end is, we look back in here, basically up to typically these first beam defining apertures. Everything accelerator on the accelerator side here is radiation protected area. So there's lots of radiation. Yeah, we are talking about kilowatt of X-rays coming out here. So this is the area behind the big concrete walls where nobody is allowed to be during operation. And then only after this so behind the front end, then after these apertures and filters, the intensity is reduced enough, and the beam is collimated well enough, such that the radiation load on people being here on the beamline is acceptably low, not to cause any radiation damage or any safety issues. Yes, so we on the front end side, where the kilowatt divergent beam comes out of the undulator, there we need these beam shaping apertures to get rid of, in particular, also these the parts of the beam at larger angles, which are typically have lower photon energies. Yeah, maybe remember yesterday or last time we discussed the angular dependence also, and typically the the regions at angles away from the beam axis are downshifted in photon energy, but we want something monochromatic and a sharp beam, so we want the central part. But yeah, these need to be quite, I mean, this is not just a little iris, as you may know it from your laser physics laboratory. because here we are talking about kilowatts of X-rays that need to be absorbed. And so these devices have to be water cooled. So for example, this is then a high pass filter that would sit just behind this aperture to like roughly filter out only the X-rays or the hard X-rays if that's what we are interested in. And that would be done with a thin diamond layer. And why diamond? Well, diamond has the property of, I think that here, yeah, diamond has the property of transmitting radiation only above a few kilo electron volts of photon energy, depending on the thickness. If we take, let's say, a 200 micrometer thin diamond layer, that would be the yellow line, then we would get decent transmission of the beam only above a few, like let's say 5 or 6 kilo electron volts. So that acts as a high pass filter. But still the heat load is very high. So this device, which like this is a typical what is called a conflat flange, where the diamond layer, that's this thin, like artificially fabricated diamond, is mounted in, needs to be water cooled. Okay, so that's the front end devices like beam shaping and filtering. Then further downstream, okay, there's some slits. Further downstream, then comes the optics, and that's the more interesting parts. So, for example, mirrors. We need mirrors to guide the beam, to focus the beam. And I mean, we have from the very beginning talked about the difficulty of building a laser in the X-ray range and of even like manipulating X-ray radiation, because there is no good materials that have high reflectivity at short wavelengths, let's say below 100 nanometer or so. That was the conclusion back then. Well, it is not exactly true. We can actually make mirrors even with high reflectivity in the X-ray, but this only works under this grazing incidence. So a typical X-ray mirror is shown here on this photograph. It looks quite different from the mirror that you might have seen in a laser lab, which is typically this 1-inch round silver coated glass substrate or so. For X-rays, we need grazing incidence to get a decent reflectivity, which means these mirrors are quite elongated. They can be meters long, which of course means that the surface quality needs to be extremely high, because the beam spreads over this very long region that's shown as this yellow elliptic profile here. And so very high surface quality in terms of roughness and wobbliness, but and also very high surface quality in terms of curvature, if this is supposed to be a focusing mirror. And we will come to these focusing mirrors in a minute. So in order to better understand how we can get high reflectivities for the X-ray, I thought it would be a good idea to look a little bit into the theory behind the interaction of light with matter. And one very simple but still very instructive model is the so-called Lorentz oscillator model, which is a purely classical model. I'm not sure if any of you have heard about this Lorentz classical oscillator model, but it's a very instructive model in optics. What it's based on is it's essentially just a classical harmonic oscillator. Which is to make it realistic, a three-dimensional harmonic oscillator to describe one single electron bound in an atom that is driven by a light field, by an electromagnetic wave. right? That's the simplest possible model assumption we can make. Of course, an electron in an atom is certainly not bound in a harmonic potential or by harmonic forces. I mean, it should be more something like a Coulomb potential, but it turns out that still this is quite a good approximation because, as in many cases, the harmonic approximation works quite well. Always when the perturbations, like when in this case, the elongation of the electron is very small. So as long as we are not driving the electron with very strong laser fields, this harmonic approximation is still quite good. So let's solve Newton's equation or look at Newton's equation of motion. Yeah? Mass times acceleration equals forces. And so we have various forces here. We have a spring force, which is supposed to be just a linear as a function of elongation. We have a damping force. This is to take into account that it's a charge in the end. The electron is a charge that is, when it's accelerated, it will emit radiation. And we have a driving force, which is supposed to be the electric field in the electromagnetic wave that we shine on this charge. So we plug in charge times electric field for the driving force. We have the linear term for the spring constant times like the spring force, and we have essentially 1 over the lifetime times the velocity as a damping force. So basically just a pure friction term. And yeah, this can be just solved or isolated for E on the right-hand side. It's the same equation as that. And then to solve this equation here, we have to make some ansatz. And the ansatz, as in many cases, would be just a wave ansatz. And this most elegant way is to use the imaginary or the complex representation of an oscillation, e to the minus I omega t. Both we make the same ansatz for the radius, so the elongation of the oscillator, and the external driving electric field. So if we put these two terms into E, like we substitute into E and R, take the derivatives, then we end up by this term here. So the elongation R has some prefactor, complex factor that depends on both the eigenfrequency of the oscillator and the frequency of the driving electric field times the amplitude of the electric field. And now we can remember that it's a charge that is elongated, charge times elongation times the spatial x vector. This gives us a dipole moment. And the dipole moment as a function of electric field can be written as P equals alpha E, where alpha is the so-called polarizability. So alpha is the quantity that tells us like how strong is the dipole moment when we apply a certain electric field, right? So if the particle is highly polarizable, it means alpha is large, meaning that already with applying some small electric field will give us a large dipole moment, right? That's what the polarizability tells us. But I mean, here it's just given by essentially this term here, this prefactor in front of the electric field with an additional E elementary charge. And now again, we should remember from classical electromagnetism that the polarizability of a single particle, like this electron that mimics the electron in an atom, that is connected to the macroscopic polarization of the medium just by taking this term times n, where n is the number or the number density of how many oscillators we have in total. And then we should remember that the electric displacement, D, is epsilon, the permittivity times electric field, which equals the electric field plus 2 pi polarizability. So the permittivity epsilon equals 1 plus 4 pi, the number of oscillators times the polarizability of each oscillator. And yeah, just from the results of the oscillator model, then we can write this permittivity, or also called the dielectric function, then as 1 plus 4 pi n and alpha, where alpha is this atomic polarizability in this simple oscillator model. Right, so this gives us the dielectric function. And by the way, this prefactor here, 4 pi n e square over m, this has the unit of a frequency square. This is called the so-called plasma frequency. If we plot this, the epsilon here, this dielectric function, as a function of wavelength, going across the omega naught, so the resonance frequency or the resonance wavelength of the oscillator that was chosen in this case to be 23.8 terahertz to mimic silicon carbide, like vibrations. This is, of course, terahertz. This is a 12.6 micrometer wavelength. This is mid-infrared, meaning vibrational excitations in silicon carbide. But anyway, it's just a simple harmonic oscillator in the end. Point is, we have, like, the dielectric function consists of two contributions. The real part, I mean, in the end, it's a complex function, right? So it has a real part and it has an imaginary part. The real part has this typical line shape. This looks like a peak, whereas sorry, that's the imaginary part. The real part has this dispersion type curve, it's called, which looks like the negative derivative of the peak function. Now, does anybody remember, or does anybody know what this orange dashed curve is called? This particular curve shape has a particular name, something like a Gaussian function, but I can tell you this is not the Gaussian function. But what's the name of this orange curve shape or curve? Has anybody seen this type of a peak function? Is it a? It's not a Gaussian. What else? How else could this be called? Any idea? What other peak
Laurentian?
functions do you know? Sorry,
Is that
Silvio. Yeah,
Laurentian?
yes, Laurentian. I mean, it's called the Laurentian because this is the Lorentz oscillator model, right? So it's all comes from Mr. Lorentz, who developed this, or who studied, I guess, this oscillator and harmonic oscillator and this resonance behavior. Yeah, this is just going across the resonance, like across the eigen frequency omega naught, where we get this behavior of the real and imaginary parts. Okay, so how is this all related to now our X-ray optics? Well, I mean, we just derived the dielectric function, and we should remember again from maybe your electromagnetism or optics course that the permittivity or the dielectric function is related to the refractive index by just dividing by epsilon naught the vacuum permittivity, take the square root, and we have the refractive index. So if we remember, this is our Lorentz oscillator resonance term here, and so on. We get this expression square root of 1 minus, and okay, here is a sum now. There's a sum because to make it a bit more realistic, now we assume that there's not only a single oscillator, but there's possibly many oscillators. Or in other terms, the electron or the atoms in our solid material may have more than one characteristic eigenfrequency. Yeah, not only one omega naught eigenfrequency, but there might be several omega j eigenfrequencies. And this is the more realistic case because there's more degrees of freedom in a crystal or in any material where the atoms and the electrons can resonate at various different frequencies. So we should take into account all these different frequency modes. And yeah, just to introduce another way of writing this, I mean, and taking into account that the leading term is the one, the unity, and then comes minus and like various, and then there's sum over complex terms, but typically all what comes behind the minus is small. So we can approximate the square root function. Typically, we can linear approximate it, and then we are just left with this small number, small complex number, which has a real part and an imaginary part. And like to draw the real part of the index of refraction, which is like when we usually talk about index of refraction of glass is 1.5 or so, then we implicitly mean the real part of the index of refraction. The imaginary part, that is what we will see that in a minute. That is what causes attenuation of radiation because of the light being absorbed in the material. But if we are just interested in refraction for now, then it's the real part that counts. And a very generic curve showing the refractive index of some material over many orders of magnitude of frequencies is shown here. And this is not any realistic material, I think. It's a generic curve, but for most materials, it looks somehow similar. So why does it look like this? So we have maybe the main trend you can say is that the index of refraction drops, right? It's in the infrared, so that would be like tens of micron wavelength. There we can easily have quite a large index of refraction, which also means that in the infrared, it's easy to make, to refract light, to make mirrors, to build lenses. Refraction is very efficient in the infrared. But you can already see that going towards the UV and then into the X-ray range, the index of refraction typically becomes very, very like close to 1. Only very small variations from 1. That's one main trend. The other main trend is that we have these wiggles, like these regions where the index of refraction actually quickly drops from large to small. This is also called anomalous dispersion, whereas the rising edges is called the normal dispersion. So normally we have increasing index of refraction as a function of frequency, but in these around these resonances, we have sharply dropping, which is the anomalous refraction, the anomalous dispersion, it's called. So where do these sudden drops, these steps, where do they come from? You can see that they are like kind of labeled by omega IR, then there's an omega UV, then there's omega KLM. So what are these frequencies where we have these sharp drops? So this is You would find that for any material more or less in this way. Can someone tell me what's happening between infrared and visible, where there's some characteristic frequency omega IR, or what's happening in the UV, what's happening in the X-ray that suddenly makes the index of refraction drop so sharply?
It's because of the resonance frequency of different
Yes,
materials, right?
absolutely, sure. I mean, we just learned from the slide before. This is exactly how it looks like going across this one single resonance in our simple harmonic oscillator. So we have these sharp like step-like behavior for the real part of the refractive index. But why at omega IR? So somewhere between IR and visible. Why in the UV? Why in the X-ray? So what kind of resonators or like resonant oscillators are we talking about? There must be some degrees of freedom that are resonantly excited. Okay, I mean here and that again, this example was just the harmonic oscillator, but it was tuned such that there is a resonance at 12.5 micrometer, which is just, or 12.6 micrometer, which is just the resonance frequency for silicon carbide. But what exactly oscillates in silicon carbide at this
Is it
frequency?
like how there's like dipole moment has a separate resonance frequency, then between the ions, and then there's one electron, there's this whole dipole moment curve which comes in different region. Is it related to that?
So you have in mind the electron oscillating with respect to the ion. Actually, in this case, yeah, that's a bit confusing. That's what I told you in the first place, that we were considering the electron oscillating around the core. That is true, but not for this wavelength or this frequency. Yeah, this frequency or this wavelength, 12.6 micrometer, is very long wavelength. It's a very slow vibration. This is not the electron that vibrates here. What else can vibrate in silicon carbide or any other solid state material? If it's not the electron that oscillates, what else oscillates? I mean, it has to be some kind of crystal. It's not silicon atoms in free space as like it's not an atomic gas. In this case, like in order to have these long wavelength, slow vibrations, has to be a crystal. So what degrees of freedom are there in a crystal? Well, I mean, if it's not the electron that oscillates, then it's probably the whole, yeah?
Atoms, ions.
Yes, it's the lattice. These are lattice
Yeah.
vibrations, right? I mean, we have these atoms or silicon carbide might, probably not very polar, but there's probably some ionic component to the chemical bond. So, yeah, there's some, anyway, it's the atoms that oscillate with respect to their lattice sites. This is also called phonons, right? Phonons is something like vibrations or lattice vibrations in a crystal. Yes, so that is typically what happens in the IR. When you do IR spectroscopy of molecules, then you would probe vibrations of the molecules. If you do IR spectroscopy or IR excitation of a crystal, then these are phonons. Yes. Then what about the wiggle at at omega UV? And what about the wiggle at omega KLM? What kind of degrees of freedom do we excite here resonantly?
Electron transitions.
Yes, right. This is now exactly what Jayesh just was mentioning before. This is now actually the electron oscillating. And in the UV, this would be the valence excitation. So something like I don't know, in sodium, for example, you have this one valence electron in the 3s orbital. You would excite the 3s to 3p. In sodium, it's indivisible, but most other atoms and molecules have their first excited states, and like the lowest transitions, electronic transitions, they would have it in the UV. So what is omega KLM? What kind of degrees of freedom do we now excite in the X-ray? Resonantly?
Nuclear transition.
These are inner shell or even core shell transitions or excitation or ionizations. And KLM, I mean, this is the naming of the different shells. The K shell is the innermost one S shell, or one N equals 1 shell, which is the 1S shell, by the way, sure. Then L is N equals 2, M is N equals 3, and so on. So yeah, these are the inner or core shells. And that, of course, takes much more energy to excite or ionize an electron out of the core shell. So this is in the X-ray range. Okay, just to understand the generic behavior of refractive index. And if we take a closer look at these parameters delta and beta that make up the refractive index, then delta and beta can be written as this, like a collection of constants. In particular, this Re it's called the classical electron radius, but this is essentially, I mean, the electron has no radius, right? This is just a collection of fundamental constants. We have the number of electrons that contribute to the oscillation, and we have, very importantly, the wavelength square. So this term, lambda square, that's what makes the refractive index in general drop down to very small values as the frequency increases and the wavelength gets shorter. Both terms, delta and beta, sharply drop as the wavelength square, which explains that in the X-ray range, the refractive index always is very close to 1. So this already tells us that, for example, building a lens that produces has a short focal length and like sharply focuses light will be very hard to build in the X-ray because the index of refraction is so close to vacuum, so close to 1. And then we have these, that's called atomic scattering factors, F1, F2. These are essentially, they contain this resonance terms. And yeah, another interesting detail is that the index of refraction in the UV, but mostly in the X-ray, can actually become smaller than 1. And that might sound strange because index of refraction smaller than 1 would mean that the speed of light is then actually larger in the material, larger than the speed of light in vacuum, right? I mean, speed of light in material is c over n. So if n is smaller than 1, then speed of light gets faster than the speed of light in vacuum. How can that be? And I mean, doesn't that violate special relativity? Well, actually not, because the speed of light only tells us about the phase velocity of the electromagnetic wave. And that can be faster than the speed of light in vacuum. But the group velocity, which actually is the velocity that characterizes transport of information and of energy, the group velocity will still stay below, so slower than the speed of light in vacuum, of course. So there's no issue with special relativity, but it tells us that, but the index of refraction becomes smaller than 1, and that has important consequences for building mirrors, for example. We will come to that. This is just to show you these scattering factors, F1, F2 for the example of carbon, for example. So there is something happening at around 300 eV in carbon, where F1 has this very sharp peak and F2 has this this sharp kink. And so can anybody guess or tell me what's happening at 300 eV with the carbon atom that these atomic scattering factors would behave this so strangely there? What's happening at 300 eV in carbon? Silvio, you should know. I think we haven't scanned across carbon also 300 eV. I mean, we have certainly scanned other K edges.
Yes. Yeah.
Yeah, so that's the carbon K edge, very famous. If you ever get to do X-ray science, carbon K edge at 300 eV, you will definitely meet that again, because like all organic molecules, all organic material contain carbon. So and carbon, so K edge means that we just pass across the K-shell ionization threshold, right? K-shell ionization threshold means we ionize electrons out of the K-shell, out of the 1s orbital in carbon, and that happens at 300 eV. Yes, and actually all these parameters, index of refraction, and so the delta and beta and all these things you can easily look up. There's a very convenient website on Livermore, I think it's LBL. So in the US, this website here, and for example, can pull out the delta and beta for nickel, which shows this overall drop that comes from the lambda square scaling. And then we see this characteristic kinks and dips. That's whenever we hit an inner shell ionization edge, right? So this for nickel, it seems the K edge then for nickel is almost at 10,000 electron volts. In gold, looks similar. Of course, the edges are at slightly different values. So we just learned that the index of refraction in the X-ray can be smaller than 1. So what does this mean for refraction? If we look first on here in the middle sketch, this shows an interface, let's say from air, index of refraction is roughly 1, into water, for example. Water has an index of refraction slightly larger than 1. Then you may know that incident light that hits the surface under an angle alpha would get refracted towards the normal, right? So alpha prime will be larger. But that has to do with the fact that water or glass, or like most materials, have a larger index of refraction than air. In the case of X-rays, it can be the opposite, right? And the index of refraction can be smaller than 1, which means that now refraction goes the opposite way. So it means that the refracted beam has a smaller angle to the surface. And it also means that just like in water, you can reach conditions when you shine light from the bottom of the lake onto the water surface at some like small angle, then you would get what is called total internal reflection, right? This I'm sure you're familiar with. In the case of X-rays with index of refraction smaller than 1, you can get an effect called total external reflection, which would be a case like shown here on the bottom right, where at grazing incidence, none of the light beams actually penetrates deep into the material, but get completely fully reflected. And that is good news if we want to build an X-ray mirror, right? Because it tells us that we just have to stay below the critical angle for total external reflection, and we get 100% reflectivity, a perfect mirror. And that is nearly true. Of course, the world is not perfect, and the light does not get reflected just at an infinitely thin layer on the surface, but still the light penetrates exponentially into the material by what is called an evanescent wave. So if the material in this very like nanometer thin surface layer would absorb the light, and X-rays unfortunately do get absorbed quite efficiently, then there would still be some losses just in this very thin surface layer due to the evanescent wave penetrating into this very top layers of the material. But nevertheless, reflectivities can be very high. And you can actually easily derive the expression for this critical angle for total external reflection, where the angles here, I mean, note that the angles are measured towards the interface, not towards the normal. And then, for this definition of the angle, we get an expression that the critical angle equals arc cosine 1 minus delta, which is approximately equal square root of 2 delta. So, little exercise for you. Please derive from Snell's law. I'm sure you all know Snell's law. I mean, Snell's law still applies here. And you may be familiar with Snell's law in terms of n1 times sine alpha 1 equals n2 sine alpha 2. Here it's cosine, but that's just because we measure the angle to the interface, not to the normal. So that's Snell's law for this definition of angles. So please try and derive this expression for the critical angle for total reflection. Or did not, it's already derived, but prove that this is the correct formula. So, and anybody who has, I mean, I can tell you it's just one line. There's not much to calculate, but it's basically about realizing what it means that the total external reflection happens. Like, what does it mean in terms of the angle? So as if somebody has the answer, then please speak up. And
small angles, right? You need to consider small angles. And
yes, how small? And which small angle? The incident angle or the like alpha or alpha prime?
alpha. Let's say alpha.
Sure. I mean, for any small angle alpha smaller than the critical angle, we would get total external. But which, like, how do we find the alpha critical? Like, what is the condition for alpha being exactly equal alpha c? What about alpha prime? But how large is alpha prime under total external reflection conditions?
Zero? I don't know. Maybe
Yes.
zero.
Yes. Because I mean, look on here on the top, we do not have a total external reflection. There's the beam still goes into the material, right? So and here alpha prime is is positive and like goes downwards. When alpha, the incident angle is smaller than the critical one, then we have external, and alpha goes the other. So at the critical angle, alpha prime is just exactly 0. basically the reflected beam travels just along the interface. So that's the only thought that you really have to put into the system. And I mean, we assume that n1 is 1, right? n1 is 1, alpha prime. The reflected angle is 0. So then inject this into the Snell's law. Cosine 0 is 1, n1 is 1, and then we get here, and just then solve for n2. And okay, assuming that beta is equal is very small, so we neglect the absorption. So beta is roughly 0, so we have only index of refraction is just 1 minus delta. All right, this is the critical angle, and so we may wonder, so how large are these critical angles for like real materials? Is this even realistic to get into this regime of total external reflection? And yes, it is, but I mean, you see here the critical angle is very small, so it's on the order of 1 degree for let's say soft X-ray and up to 10 keV, but then it gets way below 1 degree, so more like 1/10 of a degree or so for 10 keV and or 20 keV and larger. So this is platinum, rhodium, silicon, like typical materials that you would use to make a mirror. And you also see these very sharp dips. This is, of course, whenever there is any edges and yeah, any inner shell edges where then absorption and resonant excitations happen. Yeah, so that's basically to realize total external reflection is possible, but very small angles, meaning grazing incidence optics are needed. And as a rule of thumb, again, there you can simplify this, like plug in numbers, and as a rule of thumb, we get that the critical angle is something like square root of z, where z is the atomic charge, or like the number of electrons per atom divided by 30 times the wavelength. So a little exercise for gold. Gold is one of the most frequently used materials for making up these X-ray mirrors. Z equals 79 at 10 keV. What would be the critical angle for gold if we want nearly perfect reflection on our gold mirror at 10 keV? What angle should we place the mirror at? How do you calculate? Or and the formula is given here. Just plug in the numbers. Anybody has a result?
I'm getting around
37.
0.4 degree.
Yeah, 0.4 sounds good. I get something like 0.36 degrees, but yeah, I mean, just to estimate, Z is 79. This is roughly something like 81. Square root of 81 is 9. 9 by 30 is roughly 1/3. The wavelength of a 10 keV photon is, I think, something like 1.2 angstrom. So 1.2 angstrom times a third is yes, something like that. 0.4 degrees. So 0.4 degrees, this is grazing incidence. So we need, that explains why these mirrors have to be so long and placed at grazing incidence. And yeah, then if it's not exactly the critical angle, then of course we have the Fresnel equations for reflection and also refraction. Yeah, for the reflectivity. Okay, if you want to calculate the reflectivity of the interfaces as a function of the index of refraction for the incident and transmitted waves, we have these Fresnel equations that I'm sure you're familiar. And for normal incidence, we get this simple equation that I'm sure you have seen. Yeah, this is the Fresnel equations, like reflectivities for two different polarizations, S and P polarized for the interface glass to air, where yeah, there is, you can see, maybe to remind you that the transmission, so T stands for transmission, can actually become one. So perfect transmission at the interface between glass to air at a famous angle at 56 degrees roughly. Does anybody, oh, okay, it's written here. No, this is Brewster's angle, right? At Brewster's angle, the reflectivity can actually become 0 and the transmission 1, but this is for like index of refraction larger than 1. That's not the case in X-rays. Just to remind you that how to calculate the reflectivity coefficients based on the index of refraction. Of course, this also holds in the X-ray. And yeah, typical reflectivities, now that we know the index of refraction, as a function of photon energy. And I mean, why gold? Because gold is probably the most used material for building a mirror, because gold is very inert and can be made very flat and smooth. So it's very well suited for making optical surfaces. But you can see that the reflectivity is good in the range of, and that's for a degree, an angle of 1 degree. Here the reflectivity is quite okay, like 70% up to 2 kilovolts, but then sharply drops down, and above 6 kilovolts of photon energy, the reflectivity is almost 0. So no, definitely not suitable for a mirror. Here below, something like a few hundred volts, the reflectivity goes up to 1. So this is almost perfect reflectivity. But if we now reduce the angle to 0.5 degrees, then we really get very high reflectivities, even up to, or quite high, up to 8 keV or so, showing that, yeah, smaller angles help to get the reflectivity up. So another little exercise. We are working with 1 keV X-ray beam, and you want to place a gold mirror into the beam such that the reflectivity should be higher than 90%. Under what angle should you place the mirror in the beam? And to find the answer, you need to look up the reflectivity as a function of photon energy and as a function of angle. And that actually you find here, down here is the website where you can look up all these constants. So let's visit this website. Now again, the issue that I cannot see the... okay, let's go here. So this is a very useful website. You find atomic scattering factors, for example, that we just discussed. But you also find the index of refraction. So if you're now interested in index of refraction of gold, type in gold. Let's say, yeah, from, let's say, 1,000 to 20,000 volts. And submit. Okay, this is not the index, this is the delta and beta. So here you get the delta and beta curves. What we are interested in is actually index of refraction. So that would be reflectivity of a thick mirror. So let's go here, type in gold. That's 1,000 to 20,000. And you have to specify the angle. Let's say 1 degree. That's the reflectivity that you get, right? So here we have 80% reflectivity only below 2 keV roughly, and then then it sharply drops. So now it's time for you to just play around a little bit and tell me at what angle you should place the gold surface to get more than 90% reflectivity at 1 keV. Let me, to make it simpler, I will copy this link into the chat. Where do I get it into the chat? Chat. Yes, so it's in the, you can see the link in the chat. Please open the link and go to reflectivities. Yeah, remember this, so you can choose between X-ray properties of elements, index of refraction, you find delta and beta functions, but please look up the X-ray reflectivity for a thick mirror. That's what we are interested in. And we are interested in the reflectivity at, what was it, 1 keV. So anybody has suggestions about which angle should we use? Are you playing around with it or are you sleeping? I guess everyone is sleeping.
We are playing.
So where does it work? Where do you get more than 90%? At what angle? Rajni, do you have it?
Not yet.
Roughly which angle works? Have you found
I got
roughly?
it at 0.4.
0.2 it shows.
Okay, 0.2, that's very much on the safe side, but 0.2 degrees is challenging to mount a mirror. But yes, 0.4
We got
is,
0.4.
yeah, I agree. Actually, I mean, if you look at my screen again, here I plotted 0.45 in the range between 500 volts and 1500 volts. And you can see that at 1 keV, it's just slightly above 90% reflectivity. So something around 0.45 degrees seems to be a decent value. All right. I mean, this is more to make you play around with this website, because it's really very instructive or very useful if you're interested in finding out any of these optical properties of the different materials. Okay, then let's maybe continue and finalize the discussion about mirrors. So many in the X-ray, in these X-ray beam lines, very often mirrors are not just flat, but actually, since we cannot use lenses, yeah, remember the index of refraction is very small in the X-ray range, so it's very hard to get diffractive optics, that like lenses that have a decent focusing property. And anyway, if we put some lens, like try to use diffractive optics in an X-ray beam, then most of the X-rays would get absorbed and we would have enormous losses, and X-rays cause radiation damage. So we would start breaking the materials and so on. So it's much more convenient to use reflective optics, not only for steering the beam, but also for focusing the beam. And like, for example, focusing mirror is shown here, has this curved surface, which of course should be just shaped in the right way. That's something like a point source. If that's if we have something like a point source as the incident beam would then get focused again into a point in the focal plane. And yeah, these X-ray focusing mirrors actually look like that. Let's have these curved profile, but still need of course, very high surface quality. And in practice, typical profile of focusing mirrors are of this toroidal shape. What is meant by a toroidal mirror is that it's essentially a cutout from this geometric shape of a torus, which has like circular profile both in the longitudinal and also in the transverse direction. And that of course makes it easier for machining, because it's easier to machine like round circular profiles rather than something more sophisticated. But of course, the ideal shape to get a perfect focusing of a point source, again on a point object, would be an ellipsoid, because then only in an ellipse you focus the light from one focus to the next focus. But as you can see here, the circularly bent mirror, which, for example, would be the toroidal mirror that has a circular profile, is quite a good approximation, given that the X-ray beam is quite narrow and only illuminates a small part of it. And yeah, so if focusing should go in both directions, both in let's say in horizontal and in horizontal and vertical direction, then it has to have this three-dimensional profile, where you would call one radius the meridional, the other one is the sagittal radius. And you can easily calculate the focal length given the radii of curvature using these formulas here. It's nice to have such a curved mirror to focus the beam, but oftentimes you would like to have some flexibility and like ideally you would have the option to choose where exactly is the position of the focus. Like you would like to control the focal length of the mirror. And this, for example, you might also, of what often is a problem with these X-ray optics is that since these are intense X-rays, they cause local heating of the mirror surface, which again causes some thermal lensing effects. So these effects you would like to compensate by adaptively changing the radius of curvature of the mirror surfaces. And this can actually be done, for example, by these bendable silicon mirrors. And there's various ways of bending the mirrors. I mean, of course, when we talk about bending, this is not like bending it completely round, but it's bending only fractions of a degree of angle of inclination, right? Because we have seen this has to be grazing incidence anyway, so only very shallow curvature of the mirror is enough to already change the focal length significantly. And there's various mechanisms to bend. One is actually like just press on the ends of the mirror very hard to make the mirror bend. Now, this is called the end-coupled benders. Their forces are applied on the mirror ends, both push and pull. And then the mirror flexes elastically, and this produces a nearly parabolic or elliptical profile, which is okay to get good focusing conditions. But of course, the profile shaping is given just by the material, so there's no way of really adaptively changing the shape of the mirror. So more modern and more intelligent ways are by actually gluing little piezo elements into the different regions, like as segments into the mirror material. And then by applying high voltages on the piezo stacks, we can actually adaptively control at least sections of the mirror. So that makes it possible to really adaptively change the focusing properties of the mirror in so-called like multi-zone controls. And yeah, that is often used in like modern synchrotrons, but also for free electron lasers. This will be very important to get tight focusing. Just a word on surface roughness. So really we need, since the wavelength is so short, we are talking about angstrom wavelength of the light, the surface roughness has to be extremely small. So both like macroscopic wobbliness, like some like bumps on the surface, and also the atomic roughness really have to be controlled on a level of just a few angstrom. So this makes like the polishing and the finishing of the surfaces of these mirrors extremely challenging and very expensive. So these X-ray mirrors are extremely expensive. And this I can tell you from my own experience, because in my lab, even though it's just EUV, so we are not so sensitive to surface roughness, but we had to replace a focusing mirror of this type once, and that was around $15,000 of cost. Yeah, $15,000 for just one gold mirror like this. Just to give you an order of magnitude. Yeah, a very flexible and nice way of focusing in two directions is using this arrangement here, this so-called KB optics, which basically consists of two cylindrically shaped focusing mirrors, and there are two cross cylinders. that has the property that astigmatism just cancels. And so these KB optics oftentimes are made of these adaptable piezo based adaptable mirrors, and that of course gives full flexibility to optimize the focal conditions. And that is, as far as I have experience for free electron lasers, this is always the focusing system to really control the focal spot size and also try to get the XFEL beam focused as tightly as possible, if that's what you want. This is a typical way of mounting these KB optics. So you have like one grazing incidence mirror like this, and the whole thing has to be in vacuum, right? One mirror here, one mirror there. Everything has to be very stable, but still adjustable. So these are all quite sophisticated mechanical devices and bulky and very expensive. Yeah, so far we have been talking a lot about mirrors and reflection and refraction. Maybe just in the last minutes, also a word about absorption, because if we look again at our electric field or electric wave, electric field in the electromagnetic wave with index of refraction n here, but n has a real part and an imaginary part, right? The real part, that's what causes refraction that we have just talked about, but there's this imaginary part also, which was the beta in the other delta plus beta representation. And due to the fact that we have an I in the exponent, and then comes the I from the imaginary part that then gives us a minus, so we get a term e to the minus nkz. And that is a term that damps the amplitude exponentially. So if we take the module square to get the intensity, then we would arrive to this famous expression where the intensity is exponentially damped with a extinction coefficient mu, which is just given by 2n, like the imaginary part of the refractive index times k, and that is the well-known Lambert-Beer or Beer-Lambert law. Yeah, in the other nomenclature, this was the beta coefficient, telling us that when a wave penetrates into a medium that has also this imaginary component of the refractive index, then the intensity gets exponentially damped. And that leads us to looking at transmission of media. And again, transmission of media. So this is now not about reflection or refraction. This is like how much amplitude or how much intensity gets transmitted and how much gets absorbed for a light beam, for example, in this case, going through carbon. Why carbon? Well, diamond is an important material. Diamond consists only of carbon. We can choose the thickness. This is 0.2 microns. And then you can see that actually the transmission through diamond is absolutely zero up to roughly 50 EV in the in the EUV, completely opaque. Then it goes up. Then there's this sharp kink at 300 EV. Okay, we know this is the K shell, the K edge of carbon. And then for higher photon energies, the transmission rises again. That's the same carbon, only for a thickness of 10 microns, where, okay, thicker material, of course, absorbs more. So it's almost flat zero up to 1 keV. Just near the edge, there's this peak here. But if we extend the range now up to 10 keV, we see this high pass behavior of diamond that we have looked at in the in the beginning of the presentation, right? Remember, in the beginning we talked about high pass filtering radiation coming out of the undulator to get rid of all the low energy photons and only transmit the hard X-rays if that's what we want. So again, you can play around for yourself and put in different materials. For example, did I have an exercise here? No, I think I didn't have any exercise, but let me just quickly show you the website. So this is now not about reflection, but this is about X-ray transmission of a solid, for example. So let's say we are interested in carbon, diamond, from between 10 and 1000 EV. The thickness is 0.2 microns, so 200 nanometer, quite a thin layer, but yeah, that gives us this transmission curve here. So one transmission curve that Shiva Krishnan and I have been looking up very often, I can tell you, is the one of tin. Tin has the symbol SN. And so we are have been mostly interested in the EUV range, let's say from 10 to 50 EV. And there you can see that tin has an interesting behavior. It has actually the property of being a bandpass filter. It just transmits radiation around 20 EV. That's EUV, that's not X-ray, but still. And it so happens that we are interested in helium, and helium just has the lowest excited states of helium are around 20 EV. So this is a nice way to filter out only resonant radiation for helium and get rid of all the rest. So this is one important aspect of this filter transmission if you are interested in EUV experiments, which we are traditionally a lot. Okay, but now I think time is up. So, and we are almost through this part of the Beamlines where it's about filters and mirrors. Next time I will quickly talk about diffraction gratings, because this is also important. Like, how do we monochromatize X-ray radiation even more? And then, so that will be a short part of next presentation. And then I will also give a few examples of like what exciting science you can actually do once we arrive with our X-ray beam up to the sample. And then starting on Wednesday next week, we will actually look into free electron lasers. So that's the plan for now. So that's it for today. I hope it wasn't too boring and too theoretical, but I think the Lorentz oscillator model is something very useful for you to recap. And this website is a very useful tool if you ever get to use EUV or X-ray radiation. Yeah, you have seen, you can find all the optical properties of materials, you can find reflectivities, you can find transmission curves. It's definitely worth looking into that again. All right, thank you very much, and we meet again on Monday.